Okay, let's take a closer look at the standard normal distribution and specifically the so-called empirical rule. So this is generally what a normal distribution looks like, and specifically this is a standard normal distribution, and a standard normal distribution has a mean of 0 and a standard deviation of 1. And it looks bell-shaped, and it's probably the bell-shapedness for which it is famous. So now we have the empirical rule. The empirical rule essentially says that whenever we have a distribution which is normal, it doesn't have to be necessarily standard normal, it could also be a distribution which has a mean of 100 and a standard deviation of 30, then we typically observe within one standard deviation of the mean 68% of all the observations, within 2 standard deviations of the mean 95% of all the observations, and within 3 standard deviations almost 100% of all the observations, namely 99.7%. So that is the empirical rule. So again, the empirical rule relates to a normal distribution which is bell-shaped, and then it says that we have within 1 standard deviation of the mean, which is what you can see here, this green area, that is 68% of all the observations. Then within plus minus 2 standard deviations of the mean, we have now 95%, and within 3 standard observations, we have 99.7%. So this so-called empirical rule is a little bit related to another famous empirical rule, which is known as Chebyshev's rule. So there was another famous scientist by the name of Chebyshev, and Chebyshev's theorem basically says that we can always find at least 1 minus 1 over k squared percent of all the observations within plus minus k deviations around the mean. And this is only for all k greater than 1. Because if k equals 1, we'll get 0. Okay, so let's just see what that means again. So according to the empirical rule, we said, okay, if we have plus minus 1 standard deviation of the mean, okay, so then by the empirical rule, we have roughly 68% of all the observations. according to Chebyshev's rule, it is not defined for one standard deviation, but for plus minus 2 standard deviations of the mean. Okay, so this is the k here, or plus minus k, the number of standard deviations around the mean. Then by the empirical rule we have roughly 95%, and by using Chebyshev's theorem it would be 1 minus 1 over k squared. So we have to look for this k squared, so 2 squared, 4. So that would be roughly 75%, or specifically at least 75%. Okay, and then in the empirical rule we would say between plus minus 3 standard deviations of the mean. Then we have here roughly 95.7%. And now, according to Chebyshev's theory, we would have 1 over 3 squared, that's 9. Then that's roughly 89%. Okay, so but that means Chebyshev's theorem says that we have at least 75% of all the observations within 2 standard deviations, and at least 89% of all the observations within 3. And the Chebyshev's theorem is clearly more robust than the empirical rule, because the empirical rule requires that we have some kind of a normal distribution, whereas Chebyshev's theorem applies to any kind of distribution, even something which is maybe skewed like this. Okay, so that's just a note on the side that there is also the empirical rule, but also an alternative which is a little bit more robust, especially when we can be sure that we are dealing with a normal distribution. And then again, the empirical rule says within 1 standard deviation of the mean 68%, within 2 95%, and within 3 99.7%. Okay, so now I mentioned earlier that the empirical rule applies to any normal distribution. So even if, let's say, a distribution has maybe a mean of 100 and a standard deviation of 30, then this is obviously not a standard normal distribution, but just a normal distribution. But every normal distribution can be converted into a standard normal distribution by creating a so-called z-score. And the z-score is this one that you see here. So what we do is we subtract from every observation the mean, and we divide by the standard deviation. And this is also what I showed you earlier. This is something that definitely shows up in the Gaussian formula, and that's a very important concept. So the point is that if we subtract from every observation in our distribution the mean, and we divide by the standard deviation, then we can convert a normal distribution, like something with a mean of 100 and a standard deviation of 30, into a standard normal distribution with a mean of 0 and a standard deviation of 1. And all we need to do is apply that formula. Okay, maybe let's just go through a quick example. So we have here some data, and you can see that our data has It consists of 5 observations, 0, 2, 4, 6, 13. The mean is 5 and the standard deviation is 5. Okay, then in the next column I subtract from every observation xi the mean, so 0 minus 5, negative 5, 2 minus 5, negative 3, 4 minus 5, negative 1, 6 minus 5, 1, 13 minus 5, 8. And then I take this difference and I divide by the standard deviation. So then for the first observation of 0, I get a z-score of negative 1. So that means that the 0 is 1 standard deviation below the mean of 5. The 2 is 0.6 standard deviations below the means, because 0.6 times 5 is 3, 5 minus 3 is 2. Well, and likewise 4 is 0.2 standard deviations below the mean, 6 would be 0.2 standard deviations above the mean, and 8 would be 1.6 standard deviation. 13 would be 1.6 standard deviations above the mean of 5. And again, 6 would be 0.2 standard deviations above the mean, and so on. Okay, let's quickly, the most important thing is now that we see that once we convert data into z-scores, the mean becomes 0 and the standard deviation becomes 1. And let me just show that quickly in Excel. And for that purpose, we can actually just copy this data quickly. And then let's open Excel. Let's paste it somewhere in here. And then let's calculate the mean. Well, let's make everything a little bit bigger, maybe. So the mean of the xi's is equal to, in Excel, we use now average. Okay, that's the 5 in the standard deviation. So now we use the formula in Excel, standard def.s. Okay, let's do it again, standard deviation.s. Okay, so that's 5. Okay, so now we calculate the z-score, and I do that in one step. So we say this is equal to, okay, our first observation 0. We subtract the mean of 5 and we divide by the standard deviation, which is also 5. We get negative 1. So the 0 is 1 standard deviation below the mean of 5. Okay, so now I can just copy down that formula. And then we see that the 2 is 0.6 standard deviations below the mean, the 4, 0.2 standard deviations below the mean, the 6 is 0.2 standard deviations above the mean, and 13, 1.6 standard deviations above the mean. So, but the interesting point is now that after we converted everything into z-scores, the mean of the z-scores is, the mean of the z-scores is 0 and the standard deviation is 1. And here I just illustrated that using 5 observations, but the same you will get if you apply it to 10,000 observations. So that is a very important concept in statistics, which allows us to use the standard normal distribution essentially for every distribution. The only thing we need to do is we need to convert our data, which is not standard normally distributed, and convert it into z-scores. And then we can work with the standard normal distribution, and that's pretty much the power of the standard normal distribution. So since any normal distributed variable n, which is distributed with a mean that is not 0 and a standard deviation that's not 1, can be transformed into a standard normal distribution with a mean of 0 and a standard deviation of 1, probabilities for a wide range of scenarios involving normally distributed continuous data can be computed using just this single distribution that was developed by Gauss. So, and of course, this makes the standard normal distribution one of the most powerful and essential concepts in statistics. Okay, so now we already mentioned the empirical rule, and we are interested in probabilities. And when it comes to dealing with continuous variables, which is the case for the standard normal distribution, so the standard normal distribution relates to continuous data, we cannot determine the exact value of, let's say, a certain number of the continuous spectrum, but we can only identify ranges. And so what you see here is a standard normal cumulative probability table, and you still can see that in textbooks. And what you can see here is that, we said by the empirical rule, if we have a z-score of 1, that means we are now 1 standard deviation above the mean. So then what the z-table, like the one that you see here, gives you is the probability to the left of it. So let's just see, okay, so here we have the z-score, and in the first column you can see, okay, 1.0. And then in the subsequent columns you get like the second digit. So, but at the z-score of 1.1, we know from the empirical rule, if you remember, we said from the empirical rule that between 1 standard deviation we have 68%. That means between 0 and 1 I should have 34%. Well, and the area from the left to the 0, well, that's 50%. So that's why at 1.000 you can see, for example, here 84.13%. And that is what a z-table gives you. It gives you the area to the left of certain critical values, and then we can work with it and calculate certain probabilities. And we will do an example in a second. And what you see here to the right is the corresponding Excel command. So let's quickly pull up again Excel, and we will work a lot with Excel. And the command is, let's say I want to know the area to the 1. So I want to know what's the area, what's the probability that a randomly selected variable from a population comes, or has a value that is less than 1 standard deviation above the mean. Well, we know it is some 84%. We just have seen that in the table. But how do we get that with Excel? The formula that we need to use is norm dot S, that stands for the standard normal, and then we say dist. Okay. And then you say, see, okay, it wants a z-score, and I want 1. And then Excel wants to know, do you want it cumulative or do you want the probability density function value? Well, because I want the area, I want this entire area and not, this p-value here. So I have to say 1. And now we should get also 84%, which we get. Okay. We can also use Excel in order to get the z-score. So this formula was norm s.dist, and you see that the formula norm s.dist gives you a probability. There's also a formula which is norm.s inverse, so equals norm, and then you can see it here, norm.s inverse, and that asks for the probability, and if you give it the probability, then it reverse engineers to the z-score. So now if I just say I want the corresponding z-score, where you have 84% probability mass to the left, then I should get here 1, and that's what I get. So typically, of course, we work with Excel rather than tables, but sometimes it's still good to know how those tables work. Okay, so now let's do an example, and let's actually work with a problem for which we can use the z-score and the standard normal distribution probability. Okay, so there's a problem, and suppose the daily water usage per person in a city is normally distributed with a mean of 15 gallons and a variance of 25 gallons. So now we know that the distribution is normal. We write it like this, with a mean of 15 and a standard deviation of 5, because the standard deviation is the square root of the variance. Okay, so now in order to save water, the city offers a tax rebate to the 15% of residents who use the least amount of water. What is the maximum daily water usage that qualifies the citizens for the tax rebate? So, okay. So the first thing that we need to do is we need to find how many standard deviations below the mean do you have to be so that the probability mass is 15%. So I'll draw that here. So we know something is normally distributed, and we take a look here at the z-score, and we know that the standard normal distribution looks like this. So I need to find the z-score where the area to the left is 15%. So this area has to be 15%. Okay, so we should get a negative z-score. Okay. We could look that up, for example, now in such a table here. So we have to see, okay, the area to the right. Where do we have 15%? Well, that is actually the same, where I would have here 15%. So I need to find the z-score where I have roughly 85% to the left. And then I have to take the negative value of that z-score. So, okay, so I can see here At the z-score of 1, we have 84%. At the z-score of 8.01, 84. So I keep on going right. So it looks like that the z-score that I'm looking at is 1.03 and 1.04, in between there, but then negative. Because if I have to the left of a z-score 85%, that means to the right of it I have 15%. But if you take the negative of the z-score, well, then we should get something like between negative 1.03 and 1.04. And you can see that those tables are not particularly useful if you need exact data. So therefore, let's just get the z-score in Excel. So, and for this purpose, I can delete everything. Okay. So what we do is we use the formula equals norm S. So is it dist or inverse? Well, it's inverse. And then I just have to enter the probability. That is 0.15. And then close parentheses. And then you see it is indeed between negative 1.03 and 1.04. And by the way, and again to illustrate that the area to the right of a z-score is the same as the area to the left of the same score negative, we can also just use again Excel and illustrate that if I set norm S inverse, but now I say 85%, 0.85, then I get the same number but with a positive sign. But we need this one and not just limit it to 3 digits quickly. So now what I know is that in our problem, I know that the people who consume the 15%, or the 15% of the people that consume the least, they are 1.036 standard deviations below the mean. Okay, so now I can just convert that into gallons, and underneath it I'll just draw again here. So now we have everything in gallons, and it looks basically the same, so it should be symmetric. And a z-score of 0, well, that corresponds to our gallon consumption of 15, the mean. So that's the population mean of 15. And the negative 1.036 below the mean, that's where we then have the 15% probability mass. So that is also 15%. The only thing I need to now know is what is 1.036 standard deviations below the mean of 15. So that is our value that gets the tax rebate. So I just call that maybe X tax rebate TR. That is equal to 15 minus 1.036 standard deviations, and the standard deviation is 5. So what I need to do is, coming back to Excel, I need to say equals 15, and now I add plus because I have already here a negative, right? So that makes it negative. 15 minus 1.036 times the standard deviation of 5, and then I get 9.818 gallons. So this critical value is 9.818. So in other words, if at the end of the month somebody can report that they used only 9.818 gallons of water or less, then they get the tax rebate. Okay, so now in the next slide, there's again the solution. And we are given the mean of 15, the variance is 25, so the standard deviation is 5. Then we found the z-score with 15% probability mass to its left, and we got negative 1.036. Then we substitute the values and we said our critical X, the level of water consumption, is 15 plus minus the 1.036 times the standard deviation, and we get then, when it's rounded to 2-digit, 9.82. So again, a citizen qualifies for the tax rebate if their daily water usage is no more than 9.82 gallons or 9.818. And in here I also show to you graphically what it looks like when you draw it accurately. So we have here the z-score, and we can see that to the left of a z-score of 1.036, so 1.036 standard deviations below the mean, we have 15% probability mass, so this green area is 15%, and we can then convert that into our critical value, but I can see there's a typo here. It should be critical value, which is 15, not 10, but now it's correct. So and then we subtract from the mean of 15, which is underneath the 0, we have the 15, and then the blue vertical bar in the lower panel, that's our critical value of 9.82. Okay, so I hope that is clear and gave you a good idea of how we use the standard normal distribution, for example, for policy purposes, and how we can convert a non-standard normally distributed distribution into a standard normally distributed one. Okay, let's just stop here, and then let's do another example in which we use the standard normal distribution to approximate the binomial.